sizing. The estimations of the size of a plate girder normally focus on the critical aspect of the respective components. Due to the slenderness of the cross-sections of the plate girder, the following are identified to be critical. For the web, the critical aspect is the flank-induced buckling. It is related to the slenderness of the web. As for the flank, we are looking into the moment resistance of the plate girder, which is directly correlated to the cross-sectional area of the flank. And for the stiffener, we are looking into its rigidity as a support. So, the respective property is related to the second moment of inertia of the cross-sections. The size of the component can be conservatively estimated based on the following assumptions. It is assumed that there are no stiffeners existence when we are estimating the size of the web. When we are estimating the size of the flank, normally we assume that the moments are taken by the flank only without the contributions by the web. As for the stiffener, normally we assume that the intermediate stiffener acts as a rigid supports. To determine the minimum web thickness, we assume that the web stiffeners does not exist, and there is a K factor here. The K factors equals to 3 represent the plastic rotation utilized. K equals to 0.4 referring to the plastic moment resistance utilized, and K equals to 0.55 referring to elastic moment resistance utilized. It can be simply understood like this is meant for class 1, class 2 and class 3. When we design the member, normally we would like the members to be at least class 1 and class 2. To determine the section classifications, we can adopt the similar calculation process like a roll section. When the compressive flank is restrained, that means the lateral torsional buckling does not occur. There are two ways that we can use to estimate the size of the plate girder. The method 1 assumes that the flank is carrying the bending moment while the web is carrying the shear force. This assumption is best used when the maximum bending moment and the maximum shear force does not happen concurrently, and it is for a restraint beam under UDL. And the moment capacity is the only dependence on the sections of the classification of the flank, as the web does not contribute to any compression resistance. Alternatively, we may consider the girder is carrying the force in one entity. However, this method is more complicated, and it can be utilized where the maximum moment and shear force are coincident. In the existence of the lateral torsional buckling, method 2 must be used. The design will follow the design step of the rope beam, except the general steps to calculate the chi LT and the alpha LTs have to be inappropriate to the welded sections. The section property will have to be calculated from the first principle. This slide compares the equations used in the method 1 and also in the method 2. The method 1 assumes that the moment is purely taken by the flank, However, it acknowledged the entire cross-sectional area of the plate girders to be the combinations of the area of the flank and also the web. On such basis, the HW and the TW are estimated based on the equations stated here. And normally we will obtain the area of the web is about equivalent to the area of the flank. As for the second method, the moment resistance contributed by the web, which is these sections, are also taken into considerations. Because of that, the estimated HW and the TW it will be slightly different than in the method 1. This eventually leads to a conditions where the area of the web is about 4 times the area of the flank. Bear in mind that the equations given here is meant for class 1 and class 2. The FYD here represents the design strength of the flank.